All right, this is the 13.1 video. So obviously 13.1 is the first section in chapter 13. So they have on page 686 an overview of chapter 13. And so here's just basically talking about how in the past we've been dealing with what's called single variable calculus, and now we're going to be dealing with functions of several variables. So they start talking about it a little bit here in this box, but there's a better explanation of some of this stuff on the next page. So you can look at this box, but we'll look at some better stuff down here. So first is if you have, and don't worry about trying to fill in your sheet yet. I'm just going to kind of give you a little bit of an overview right now, and then we'll look at specifics for your sheet in just a second. So don't worry about trying to do the sheet yet. But here, just so you can see what they're talking about, if you have a function of two independent variables, x and y would be the independent variables, and z would be the dependent variables. The domain would be a region in the xy plane. If f is a function of three independent variables, that would be x, y, and z. The dependent variable would be w, and the domain is a region in space. And so basically, let me just show you on another piece of paper. Hold on. Now you can start working on filling in your sheet. So if you had f of x, let's start there. F of x. You know from, I don't know, algebra, wherever you first saw this, that's the same thing as y. And so the domain of that would be just x's, right? So one-dimensional. And the range would be y's, so also one-dimensional. And then the graph would be in the xy plane, so two-dimensional. That you already know. All right, so new stuff. Now we're going to have f of xy. That's going to be equal to z. So our domain is going to be ordered. How does your book write it? Let's see. The set of all the ordered pairs such that, and then some condition here. So this is called set builder notation. And then there's just some condition here on the x and y. So the domain would be two-dimensional. It would be what the book was talking about, a region in the xy plane. But the range, it would be z values. So it's one-dimensional. So domain is ordered pairs. That's sets of ordered pairs. So that would be two-dimensional. Range is z, so it's one-dimensional. What is all this stuff? Oh, that's just, sorry, seeing what that paper was saying. That's just my random comments from previous videos. And so the graph, and you've been doing some of this already, but the graph of this would be in 3 dimensions, because it would be in XYZ, in the XYZ space. Okay, so if you had something like XYZ, that would be W. This is what the book was talking about. Again, at the bottom, page 686. The domain now, and in your book they said we can picture the domain as a region in space, but it would be the set of all the ordered triples such that blah, 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 some condition is met. So the domain now is three-dimensional, but the range would be W's, so it's one-dimensional. And then you can't do this on paper here, but the graph would be now four-dimensional. Okay, so you can't really draw 4 dimensions, but the graph would be four-dimensional. Okay, so notice the ranges are always one-dimensional. The domain is always however many dimensions that you have independent variables. So one independent variable, domain is one-dimensional. 2 independent variables, domain is two-dimensional. 3 independent variables, domain is three-dimensional. And then the graph is how many total variables you have, right? So I have x and y, independent, dependent, 2 total variables, graph is two-dimensional. Here I have 2 independent variables, 1 dependent variable, 3 variables total, graph is three-dimensional. And then here I have 3 independent variables, 1 dependent one, so the graph, if I could do it, would be four-dimensional. Okay, so that's kind of just an overview, and you can extend that, obviously, higher and higher dimensions, but we're pretty much not going to go past the three-dimensional graphing, obviously, because you can't graph in 4 dimensions. So this is page 687. This is a picture kind of what's going on. This would be our most common situation where we have z equals a function of x and y. So the domain, because there's 2 independent variables, the domain is two-dimensional. So the domain is some region in the xy plane, which is like this tannish blob, I don't know. And so what it's doing is it's taking ordered pairs and it's mapping them to z values. So it's two-dimensional domain, one-dimensional range. It's just sending what was ordered pairs to over here to be single z values. Okay, so down here they talk about the domain and range in better terminology than what they had in the box. So here, the domain of a function is assumed to be the largest set for which the defining rule generates real numbers. So in other words, all of the stuff that you can plug in, but it's you have to watch the dimensions, right? So like, for instance, let me show you an example. Hold on. All right, so say your function f of xy was 1 over x plus 1 over y minus 2 maybe, right? So you can plug in anything you want to as long as the x coordinate is not 0 and the y coordinate is not 2, because you don't want zeros in the denominator, right? So there's restrictions there. But if you had something like this, well, then you can plug in whatever you want to. So before in algebra, when you were allowed to plug in whatever you want to, a lot of people wrote this, or all real numbers, which was fine when the domain was one-dimensional. But the domain here is two-dimensional. So if you write this, that's wrong, because this is one-dimensional, the domain here is two-dimensional. So what you could do is write r squared, which is all real numbers by all real numbers. So it makes like all real numbers on the x, all real numbers on the y, and so it makes two-dimensional xy plane. Or the set of all ordered pairs xy, right? Because it's two-dimensional. So every possible value for x and every possible value for y, when you put those together to make ordered pairs, every possible ordered pair. So you have to be careful. Don't use all real numbers, or wait, here's another one that some people do. That also is one-dimensional. So all of this is one-dimensional, and that's not going to work anymore. So you've got to write it in words, or you've got to write it where the r represents the dimension or something. But none of that one-dimensional stuff is going to work anymore, so don't do that. Okay, and then they talk about the range. Well, this is not a very good definition because it's like, duh. But it says the range consists of all the output values. So basically, it's all the answers that you get out. The domain's all the things you're allowed to plug in. Range is all the things you're allowed to get out. But again, watch the dimension for the domain, because the dimension for the domain is going to change. Okay, and then here they're talking about interval notation. Sorry, my book is, I don't know if you can see all this nastiness in my book. My skylights in my sunroom, do you see them? Skylights. They leak when it rains sometimes. I need to replace them, but haven't gotten around to it. So I have my book under the skylight one time when it rained, and it leaked. And so all of this highlighting just kind of made this yellow river across my book. So, sorry. Thanks, skylights. Appreciate it. Okay, page 688. Here's some, there's a ton of definitions in this section. I hope you like vocabulary. Here, it's talking about interior points and boundary points. So basically, just the non-math definition, interior points are inside, boundary points are on the boundary, obviously. But the math definition here, it's an interior point if when you draw a disc, well, let's look at the picture. When you draw a disc around it, then the whole disc is inside the region. It's a boundary point if when you try to draw a disc or circle, that's their fancy way of saying circles, but if you draw a disc around it and not all of the disc is in the region, then it's a boundary point. So that's the math definition. So you can see a couple more examples here. So interior, the interior of a region is all the interior points. The boundary of a region is obviously the boundary. And so these are important definitions here. Open and closed. A region is open if it consists entirely of interior points. So in other words, there's no boundary points. So if you drew it, let's see if they have one. Do they have one? No. If you drew it, the boundary would be dotted, right? So like when you were doing this in algebra and you had to draw a region and it with an inequality and you were shading, if it was like less than, then you would shade inside the region, but the boundary itself would be dotted because the boundary wouldn't be included. That's what it means to be open. So it's open if it consists entirely of interior points, or in other words, it does not have any of its boundary points. And then it's closed if it contains all of its boundary points. So that would be like when you drew it, if you made a solid line, around the outside. So if it contains all of its boundary points, it's closed. If it doesn't contain any boundary points, so just interior points, then it's open. Because a point has to either be an interior point or a boundary point. It's got to be one or the other. Okay, and so here's a little bit more information about interior and boundary points. And here it's talking about sometimes it could be neither open nor closed, because sometimes it may contain some boundary points, but not all of the boundary points. And so that would be neither. And then here, bounded, here you're talking about regions. So you're talking about two-dimensional stuff here. So a region, which is two-dimensional, is bounded if it lies inside a disk of fixed radius. So basically, if you can draw a circle around it and contain it all, then it's bounded. If you cannot draw a circle around it and contain it all, then it's not bounded. So like, and here they didn't do it, but it should be dotted, 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 dotted all the way around here. So that should be dotted. So this, because it's dotted, 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 dotted around it, that would be open because it doesn't contain its boundary points. This would be closed because it does contain its boundary points. But both of them would be bounded because I can draw a circle around them and contain them all. So open, closed, both of them are bounded. Okay, something that would be unbounded is something like this, because see how it goes up, 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 up. So there's no way you can draw a circle around it and contain the whole thing. So that would be unbounded. So a lot of people get those confused. So make sure to notice the difference. This is open because it doesn't have the edges. Closed because it does have the edges. They're both bounded because I can draw a circle around them and contain the whole thing. And this would be unbounded because I can't draw a circle around it and contain the whole thing. Okay, so all of this is on page 688. So you can look at these. And so they give some examples down here about bounded and unbounded sets, what's bounded and what's unbounded. Okay, but now let's look at the next thing that's in this section, which is level curves. So they talk about here a couple different ways to graph something that's a function of two variables. So you can graph the three-dimensional picture like we were doing in 11.6, right? 11.6, we were graphing things that had x, y's, and z's. We were getting things like ellipsoids, hyperboloids, paraboloids, things like that. But what you can also do is you can also graph what are called, well, I thought that was level curves. Anyway, they're called level curves. Here it's talking about labeling curves. So level curves would be, so look at like this one, for instance, this paraboloid. If you took a plane and you sliced through a three-dimensional surface, then see how when you slice through this way, it's just making a bunch of ellipses or circles. I can't tell. Where's the equation? I think they're circles, but we'll go with ellipses just in general. So it's making all of these. Did I have a picture? No. But here's some of them. It's making all of these curves. So it's kind of like, I don't know, you guys are probably way too young to remember this, but they used to have those cups that you could squish them flat and they made a bunch of like rings, or then you could stretch them up and then it was became a cup when you stretched it out. And so all those little rings, when you're squished flat, that would be like level curves. And then the whole surface would be the three-dimensional surface. So they talk about this on page 689. Level curves, if you take a function of two variables that's normally equal to z, but in place of the z, you plug in numbers. So like plug in 0, plug in 1, plug in 2, whatever. Then what's happening is it's, instead of it being x, y, and z, so three-dimensional, it's now x, y, and a number. So it's two-dimensional, which is exactly what we were doing in 11.6. In 11.6, when we would break it down into the three different planes and we would replace one of the three variables with a 0, that was getting it down to be two-dimensional. That's what we were doing. But here, you're always doing them in and parallel to the xy plane. So it's always the z that you're plugging in numbers for. And that's going to give you level curves. And then I don't know where the definition is. But when you put a bunch of level curves together, you get what's called a contour map. So a contour map is made up of several level curves. You put several level curves together. I usually ask you for about 5. Several level curves together make up a contour map. Okay. And then if you graphed three-dimensionally, so like here the whole paraboloid, that would be called the surface. And then if you graphed these two-dimensional curves, which in this case are circles or ellipses, those would be the level curves. Okay, so level curves, if it's a function of two variables, they're two-dimensional. And the surface, if it's a function of two variables, is three-dimensional. Okay. So they talk about here contour curves and elevation and things like that. And then here it is if it's in higher dimensions. So you could take a 4-dimensional surface, which you can't really see, but if you had a 4-dimensional surface and you sliced it through, then you would get 3-dimensional. Well, I don't know what it's called in 4 dimensions. It's not called a surface. I don't know, a 4-dimensional thing. Slice through it, then you would get 3-dimensional surfaces. So it talks about more of that kind of stuff on page 689. So I know you can't really tell where I highlighted because of my yellow highlighting river mess from my skylights leaking. But anyway, just basically read the whole section because there's stuff everywhere. But one thing, I don't know if you've seen things like this, but here's a real life contour map. They use them for elevation a lot of times to depict mountains, which obviously they have height on it, but they're depicting them on 2-dimensional paper. So they're showing heights of mountains, hills, whatever, or valleys even, in a contour map on a 2-dimensional paper. So that would be where you would use something like this, obviously. Excuse me. And then here they're just extending the same kind of things that we've just been talking about to higher dimensions. And then we're not going to do this, but just if you're interested, they talk about here how you could do this really well on a computer. But what I do want to look at, this is the bottom of page 691, is just the connection between some surfaces and their contour maps. So surfaces, again, are the 3-dimensional pictures, and the contour maps are the 2-dimensional pictures. So it would be kind of like if you smushed it flat. All these rings are what's getting made. And so here you can see there's these several humps, and so those humps are corresponding to these circles here. Here you just have 2 humps, and so that's what's going on there. And then here it's all this kind of twisted mess, which is making these. And so they have several more pictures in the homework. The 31 to 36, they give you the contour maps, and then you're trying to match it with these pictures. So you can practice with that there. Okay, so let's see if there's anything. Yeah, so basically, I know probably a lot of you don't read your math book, but this section has a huge amount of stuff in it, and functions of several variables are what we're going to be talking about pretty much for the rest of Calc. So it's really important that you understand it. So I would just start on page 686, starting up here at the overview, and I would just read, hopefully your book isn't as messy as mine. I would read all the way until you got to computer graphing on 691. And so if you'll read that first, then what we're going to do makes a lot more sense. So if you want to, go ahead and pause your video and read it real quick and make sure you've got all of your definitions and variables and whatever filled in. And then we'll come back and look at some examples. All right, so hopefully you've read. Now we're going to look at some examples. The first group of problems, 1 through 4, it says find the specific function values. So this is just getting you used to the notation that they're using for functions of several variables. Notice in these two, it's functions of 2 variables. Here it's functions of 3 variables, and then you're just plugging in these ordered pairs, and here ordered triples. So I just did a couple of those for you here. Number 2 is a function of 2 variables, sorry. The graph would be 3-dimensional. So the first one obviously is x, the second one is y. You're plugging them in, simplifying, and so that would be a z value, right? Because f of x, y is equal to z. But number 4, oh, that was part A. Sorry, that was part A. Number 4, it's a function of 3 variables. So I did part C. So the first one is x, second one is y, third one is z. Plug them in, and then notice that would give you a w value. So f of x, y, z is w. Sorry, I had to scoot my chair up. Okay. Next, number 6, new set of directions. Find and sketch the domain for each function. So basically, what are you allowed to plug into this function? So just real quick, a little overview of domain. When you have a square root, you have to make sure the thing under the square root is greater than or equal to 0. When you have a log, you have to make sure the thing you're taking the log of is strictly greater than 0. And when you have a denominator, you have to make sure that the thing in your denominator is not equal to 0. Okay, so that's kind of the main things you're looking out for. So number 6, I have a log. So the thing I'm taking the log of needs to be greater than 0. So I set it greater than 0, move the 4 over. That would be a circle. So it does not include the surface of the circle, or the edges of the circle. And it includes all the points outside of it because it's greater than or equal to. So I would draw the circle but make it dotted because it doesn't include the points on the circle itself, and then shade everything outside. So most of these are going to involve inequalities. if they involve inequalities, the graph is going to need some shading. So don't forget to do the shading. And then I've stated it here in words. It's all the ordered pairs that are outside the circle. Okay, so that would be just kind of describing it in words. You could also do it in set builder notation. And it would be that same thing we were talking about, you know, curly brackets, ordered pair, such that, and then you would just use x squared plus y squared greater than 4. Okay, so let's look at the next group of problems. 13 to 16, find and sketch the level curves. So level curves, remember, that's what you would get if you would replace the z with numbers. And so here they actually give you the numbers they want you to replace it with. So we're going to do number 14. So here was my function. And so f of x, y is the same thing as z. So this would be like z equals x squared plus y squared. So in place of the z, I'm plugging in all these numbers that they gave me. So if I plug in 0, the only thing that's going to work there is if both x and y are 0. So that's got to be just the dot, the origin. And then for the rest of these, see how these are just circles? Radius 1, 2, 3, 4, 5. So when I put that all together, there's the dot, that one that was in the middle. And then they're just circles of different radii. So notice here, if you replace this f of xy with a z, so put a z there, then you could graph this like we were doing in 11.6, and it would be a circular paraboloid. That's what it would look like. And so this is the level curve, or kind of the smushed down version of it. Okay, next, 17 to 30. Wow, that's a big group. 17 to 30, lots of parts here. Find the domain, find the range, describe, and this is in words, describe in words the level curves, find the boundary of the domain, determine if it's open or closed or neither, decide if it's bounded or unbounded. Okay, so we have a square root. For square roots, you need the thing under the square root to be greater than or equal to 0. So if I solve this for y, it's this. So I didn't graph it, but that would obviously involve, wait, no, just kidding. I did graph it, see? That would involve shading. Okay, so it's all the points on or above the line. So because that was the or equal to. So it's the set of all the ordered pairs on or above the line. Okay, now for the range is the answer. So in other words, if you plug in ordered pairs here, what kind of answers are you going to get? So obviously this, because it's a square root, is going to be greater than or equal to 0. And so that means your z is going to be greater than or equal to 0. So remember, this is a function of two variables. My domain is 2-dimensional. My range is 1-dimensional. Okay, level curves. I'm going to pretend like this is a z, and then I'm going to replace the z with different numbers. Okay, so I made it a little bit easier here first. This is that. I replaced it with a z, and then to get rid of my square root, I just square both sides. So square both sides, the square root goes away. That becomes z squared. So z is what you're plugging numbers in for. So they call it c in the book. So I'm calling it, you could have just said z equals 0, z equals 1, z equals -2, but since the book calls it c, that's what I'm going to call it. But whatever, it doesn't matter. So I just picked these randomly, 3 numbers here. And so plugging it in for the z. And so here I get y equals x. Here I get y equals x plus 1. Here I get y equals x plus 4. So those are just a bunch of lines. And all of the lines, notice all the lines have a slope of 1, but different y-intercepts. So if I have to describe them in words, they are lines. That would not be enough information though, so don't just say they're lines. They are lines with slope 1, and then their y-intercept has the form that, notice whatever it was that I plugged in for c, the y-intercept is c squared. So they are lines of this form. Okay, and then the domain we just talked about in part A. And so the boundary of the domain would be that line. And it does include its boundary points because that line is solid and not dotted. So in part E, because it includes all of its boundary points, it would be closed. Okay, so it is a closed region. However, because if you tried to draw a circle around it, you could not contain all of the points because this just keeps going like this. So it would be unbounded because you cannot draw a circle around it and contain all of the points. Okay, so remember, closed, it contains all of its boundary points. Bounded would be if I could draw a circle around it and hold it all, but I can't. So unbounded. All right, moving right along. This is a long section. Same thing, but we're going to do another problem. So this is 26, but same directions. So here's what I would like for you to try. Number 26 is the one we're going to do. Same A through F. So pause the video, try this one by yourself, and then come back and see if you got it right. Okay, so pause it and try it by yourself. Okay. Did you cheat or did you actually pause it and try it by yourself? If you paused it and tried it by yourself, good for you. If you cheated, shame on you. Okay. Part A was the domain. So basically, what are you allowed to plug in for X and Y? Well, in a power of an E, you can have whatever you want to. So don't put all real numbers. If you put all real numbers for the domain, that's wrong because all real numbers is one-dimensional. This domain is two-dimensional. So you can say it's all points in the XY plane. You can say it's all possible ordered pairs. You can say it's R2, but you cannot say it's all real numbers. Okay, now for the range. So here, I kind of wrote an explanation. The range is kind of tricky. No matter what X and Y are, because they can be whatever you want them to be, because this is an E, E to anything is always going to be positive, meaning it can't be 0 and it can't be negative. Because if you look at the graph of E to the X, it's always strictly above the X, strictly above the X-axis. It doesn't actually touch the X-axis. So it's always, there's a vertical asymptote. That's the word I was looking for. There's a vertical asymptote at the X-axis, so it never touches it or crosses it. But here, because this is negative, if X and Y are both 0, then this would be E to the 0, well, E to the negative 0, which is still 0, and that would be 1. But for anything else, X squared, no matter what X and Y are, because you're squaring them, this is positive plus a positive, so this is always positive. But then this negative out there makes it always negative, and so this is always going to be negative. That's going to put the E in the denominator because it's E to a negative power, so the biggest that it could possibly be is 1, because everything else it's going to be smaller. So it always had to be strictly positive, but because of that negative sign, it's never going to be bigger than 1. So the range is between 0 and 1, not including 0, but including 1. All right, and then level curves, you're going to replace the f of xy with a z. Pick numbers for the z, but keep in mind, because the z can only be between 0 and 1, you can only pick things between 0 and 1. So you cannot pick 0, but you can pick 1, you can pick a half, you can pick, fractions. So I picked 1 and a half. And then here, I took the log of both sides. ln of, well, this one I didn't actually show the work for because we talked about it up here. But here, ln of 1/2, ln of this cancels out the e. So here that was an approximation of ln of 1/2. I did that on my calculator. And so notice I get a negative here and a negative here, so they cancel, and this is a circle. And so here, on the left, you're always going to have ln of the c, whatever number you picked. Ln of c is always negative whenever you're picking c's between 0 and 1. So all of these level curves are going to just be circles, like this, centered at the origin, where this is ln of c. Okay. All right, and then the domain was like, hold on, let me draw it. If you had to draw it, because it was all the ordered pairs, you would draw it. Here's the xy plane, and then it's all this, right? It's the whole xy plane. So there's no boundary on the xy plane, so it's all interior points. So if it's asking for the boundary, there is no boundary because there's no boundary points. It's all the interior, so none would be the answer to that. And then this one's a little tricky. This is one of those loophole kind of things. It's a loophole. So this is technically both open and closed, and I'll show you here why. The definition to be open means it consists entirely of interior points. We'll check. It consists entirely of interior points. We just talked about this. However, closed means that it contains all of its boundary points. Well, if it doesn't have any boundary points, that's kind of a loophole, and it sneaks in there. Politicians would love this. So it doesn't have any boundary points, so you can't say, well, it doesn't contain its boundary points. So anyway, this is kind of one of those dumb things, but you just have to go with the flow. So you would say it's closed because it doesn't even have boundary points for you to check to see if they're in there. So this is both open and closed, which is kind of weird, but it is what it is. Okay, and then if you try to draw a circle around the whole xy plane, obviously you cannot contain that in a circle, so this would be unbounded. All right, so hopefully that makes sense. I know that was a little weird with the part E, and the range was a little confusing, but that would be, kind of bonus level stuff, I think. But I wanted to show it to you anyway. Okay, so now we're doing the matching. We have 6 level curves, not level curves, contour maps made up of level curves, and then we have 6 surfaces. Sorry, my brain just died. 6 surfaces. So I did the even ones. You have to do the odd ones. So this one is the first one, 32. 32, see how it looks like it's got something going on in the middle, like a high point or a low point in the middle, and then it's got all these little, I don't know, what's the word I'm looking for? I don't know, like hills and valleys kind of a thing. Hills and valleys going on around here. There was a word I was looking for and I couldn't think of it, but hills and valleys we'll go with. So it would not be any of those. However, when you get down here, see how it's kind of something going on in the middle. It's got this flat thing in the middle, like this valley region. And then it's got all these hills and valleys all around here. So that would correspond to all these things, all those hills and valleys. And then there's something going on in the middle is this valley type region. Okay, 34. Notice you have all these circular things, which means it's either coming up or it's going down. But there's something going on that has a raised up or a going in thing in the middle. And so if you look with the only thing that has a raised up or lower down thing in the middle is this one. So it's got this raised up piece. And so if you squish that flat, that's what's making all of these ovals. And then lastly, sorry, my pages got stuck together when my skylights leaked on my book. And so when I pulled them apart, it pulled off some of the ink. So lesson learned, don't leave your book under skylights that leak when it's going to rain. So you never know what you're going to learn. And that's what I learned recently. So okay, here you have the same kind of thing, very gradual types of hills or valleys going on. See, there's like 4 of them, very gradual because of this. So I'm looking for something with 4 very gradual types of hills or valleys. And so that's what this part B is. See how it's very, very gradual, all 4 of those, and they correspond to these 4 regions. So you have to do the odd ones yourself. So again, it's just kind of a matching game. All right, now let's look at the next group of problems. This is page 693. It says, display the values of the functions in 2 ways. A, by sketching the surface, and B, by drawing an assortment of level curves and label it with its function value. So when I ask you for level curves, I usually ask you for anywhere between 3 and 5. So I would just practice on your homework doing 5, so you're good whether I ask for 3 or 5. Okay, so 44 is the one we're going to do. 44, f of xy is the same thing as z. So this is a plane since everything's linear, so it's a plane. So the easiest way to graph a plane is to find the intercepts. So for the x-intercepts, you let y and z be 0 and so on. And then when you find the intercepts, 3, 2, and 6, you can put them on there, 3, 2, and 6. And then, this is just a little trick for graphing planes. If you connect the dots like this, obviously that's a triangle, and a plane is like a sheet of paper, so it doesn't look like a triangle. But what this is it's the section of the plane that's in the first octant. So it's the, like if you cut it off with the 3 main planes, this is the part that's in the first octant. So it's not the whole plane, but that's typically how you graph planes. You just graph the first quadrant portion of it. So that's a fast and easy way to do it, is to find the intercepts and then just connect the dots. All right, but for the level curves, in place of the z, we're going to plug in different numbers. So I just picked some numbers that would work nicely with the 2s, 3s, and 6s. So 0, 3, and 6. Solving for y so I can graph them. I get, notice all of these, my slope is always negative 2/3. And then my y-intercept varies. And so these would be lines. So here's where c is 0, c is 3, c is 6. And they all have a slope of negative 2/3, so they're just a bunch of parallel lines. So that would be an example of 3 of them you could do. You don't have to show the work. If I asked you for 5 of them, after you did a couple and you realized, hey, these are all lines and they all have slope negative 2/3, you could just draw 2 more and then that would be 5. So once you notice the pattern, it's easy. Oh, I cheated. I showed you 42. Don't look. Don't look. Erase that from your mind. I want you to try 42 by yourself. So cover up. Here's the problem. 42, same thing. Part A, sketch the 3-dimensional surface. Part B, sketch the level curve. So pause the video, try this one by yourself. Okay, so hopefully you didn't cheat and you paused the video and you tried it by yourself. This one is an 11.6 problem, right? It's a circular paraboloid, so you could do that with the 3 2-dimensional pictures, right? XY plane, YZ plane, XZ plane. And you would have gotten 2 parabolas and a circle. Okay, so the 2 parabolas are there, and there, and the circle is here. And so what you should be able to do is visualize, if you squished that flat, what its level curves would look like. So if you draw, or if you pick some, 0, 4, and 3 is what I picked, just so that my numbers over here were nice for doing the radius. But notice you can't pick anything smaller than 0, and you can't pick anything bigger than 4, because if you do, it's not going to work. Okay, you can try it, but it's not going to work, because it's only just this part here of this. And so you have 3 circles. Ooh, there's a squirrel. Look at the squirrel right outside my door. Hello, squirrel. I don't know what it's doing. I hope it doesn't try to come in. I don't like squirrels. They creep me out. Chipmunks are cute. Squirrels, creepy. But they're practically the same, so I don't know what's the difference. I think it's the tail. The tail is what gets me. Oh well, bye squirrel. Back to math. So anyway, here's your circles. And that would be, again, for, well, technically that's just 2. That one is a dot. It's not really a circle, but that was corresponded to the 3 values that I picked. So 1, 2, 3. All right, let's look at a couple more. Here, 49 to 52, you want to find an equation for and sketch the graph of the level curve that passes through the given point. So this is a specific level curve that you're picking here. And so you have, where am I? Here I am, sorry. The squirrel's got me distracted. Okay, it left. Good, creeps me out. Here was the function. This is number 50, by the way. Here is the function of 2 variables. Here is the point. And then I plug in the point into the function. So there was no y to plug into, but if there was a y, I would put a 0. But I plug in the x and I get 0. So what that's telling me is at this point, at this ordered pair, z is 0. So that would correspond to the order triple, 1, 0, 0. Okay, so z is the same thing as f of xy. So if z is that, and I know z is 0, then I can solve for x. So add the x to both sides, take the square root, don't forget the plus or minus. And so the equation for the level curve when c is 0, there's actually 2 of them. It would be x equals 1 or x equals negative 1. So in other words, if you took those planes, if you take the plane x equals 1, which would be a vertical plane, 1 unit in front of the yz plane, and you use that plane and you slice through the surface here, then the level curve that you would create is the one that we were looking for. Or similarly, if you go back 1 and draw that plane and you cut through the surface, and that would give you another of the same level curves we're looking for. All right, so you try this by yourself. The next one, pause the video, try it by yourself. It's 52. So same thing. You're trying to find the equation for the level curve, or the equation that would give you the level curve through this point. Okay, so pause the video, try this by yourself. All right, so hopefully you already tried it. First you start by plugging in the point and finding the z value. So plug in the point negative 1, 1, and I get 3 for my z. So at that point z is 3. So I put a 3 in place of the z, and then I'm solving, so I multiply by x plus y plus 1 on both sides. Distribute the 3, solve for the y, and so that gives me a line. I mean, not a line. It's a line in 2 dimensions. This is a plane in 3 dimensions. So that will correspond to when c is 3. All right. So hopefully this makes sense. If you have any questions, just send me an email.